offset as well. So this offset is always attached to the non-inverting input. So you have a plus here, minus here of the value 2 millivolt here. And we also told that there's a current, right? And this current here are each of 100 nano, right? Each 100 nano. So I plus is equal to I minus is equal to I bias is equal to 100 nano because I offset is 0. Right? Since I offset is 0, I plus and I minus are equal. Alright? What else do we know? And we also know that R2 over R1 is equal to 2 because it's given to you, the gain is 2. Alright? And then we are told that the two input V1 and V2 are 0, so we ground this 2. Alright? And therefore we are asked to find out the voltage at the output, the maximum DC voltage at the output. So basically we want to find out V out DC due to the three source. So V out due to V offset plus V out due to I plus V out due to I minus. So this is what we want to find out. That is at the output due to this 3 DC component. So let's take a look at how we evaluate it. So V out, when we are dealing with V offset, I plus and I minus are 0. Right? So if I plus and I minus are 0, then I plus 0 means there's no current flowing through R1 or R2. Therefore, there's no voltage drop due to this current at this node. So this is 0. But because there's an offset, the voltage at this node will be 2 millivolt at this node. At the same time, there's no current flowing through I minus. So there's no current contribution in any of this loop except for the signal that is appearing at this node. Right? So this signal 2 millivolt now appears here. And because of this 2 millivolt appearing here, there is a current that's flowing through R1 given by the offset divided by R1. And this same current flows through R2. And therefore the voltage at the output is due to the voltage drop across R2 and the voltage drop across R1. And therefore basically it is the non-inverting gain that you have at the output. So you have V offset, V I naught divided by R1 to give you the current in R1. Take this current, multiply by the resistor R2, get you the voltage drop across R2, plus the voltage drop across R1, which is still VI naught, gives you the voltage VI naught to the output. Alright? Plus I plus to the output. When we kill I minus, we kill V offset. I plus goes through R1 and R2 that is in parallel. Right? And this voltage appears at this node. Now since current is flowing out from ground to satisfy this current source, the voltage at this node will be more negative than ground. That caused the voltage at this node to be I plus times the parallel impedance of R1 and R2. Right? And therefore it is minus, alright, I plus times R1 in parallel R2. So this component appear at the non-inverting input, and therefore it will be multiplied by the non-inverting gain that you have derived up here, which is R2 over R1 plus 1. Alright? So that is the voltage I minus appearing at the output. Alright? Voltage due to I plus appearing at the output. Alright? And then you add up with the voltage that is contributed by I minus. When you're dealing with I minus, you kill I plus, you kill V offset, and therefore there's no voltage contributed at this node, so this is 0. Now since this is also killed, so the voltage at this node is 0. Now since this voltage is 0, this becomes virtual ground. Then since this is 0, this is virtual ground, there's no current flowing through R1. This current has no choice but to flow through R2. As it flows from right to left, it incurs a voltage that is more positive here than here. But since the negative value goes to ground, then the voltage at the right side of this resistor is virtually the voltage across the output. And therefore the voltage at the output due to I minus will be I minus times R2 to the output. So this is the total voltage at the output. And now you can evaluate what the voltage at the output DC is. So this is equal to V I naught into R2 over R1 plus 1, all right? And minus I plus R1 in parallel with R2, so you multiply them out. Multiply by the non-inverting gain, which is R1 plus R2 over R1, all right? And then you add up with I minus times R2. Okay? Over here you can start cancelling this and this and this. What is left is this being 2 millivolt, all right? And this being a gain of 2, so 2 plus 1. And this being minus I plus R2 plus I minus R2. Now since I plus and I minus are equal, all right, and therefore these two terms cancel off, and this becomes 6 millivolt. Okay. So what happens if the DC offset voltage is 0? So if the DC offset voltage is 0, then the output DC will be 0, because the DC input voltage will not have, since the DC, if we say that the DC offset input voltage is 0, then this term will not be there and this 2 will cancel out, correct? And this is exactly what we have done. Remember we did in the class, we found out that if the two currents are equal, all we need is to introduce a resistor at the non-inverting input of the value Rx. Remember? Yeah? And what is the value of Rx? The value of Rx, when you look out, is the parallel impedance of R1 and R2. So look out from here, you see R2 and R1 in parallel. So if the two resistors seen by the two input looking out is the same, then the two current that's going through it, if they are the same, will incur the same voltage, and therefore the difference of the two voltage is 0, and therefore when multiplied by the gain will give you 0 at the output, which will then cancel out, right? So if there's 0 offset input voltage, then the output will cancel off because the input current are the same, and we make the resistor value equal, it will cancel off. Okay? Any question? Now let's take a look at question 2. So this is question 1. In question 2, we are given an op-amp that is non-inverting. All right. Sorry. And we have a resistor Rs connected to the non-inverting input through a source Vs. All right. And we are asked to find out the voltage at the output, Vout, right? When this is R2 and this is R1, and the op-amp is treated as ideal, and therefore we can find out the voltage at the output. Basically, this is Vs into R2 over R1 plus plus 1, non-inverting gain. Agreed? So this is part A. This is part A. Realize that the resistor Rs does not play a part. Why? Because there's no current going into the input, because we are treating the op-amp as ideal. Okay? Since we are treating the op-amp as ideal, there's no voltage drop across Rs, therefore the voltage Vs appear directly at the non-inverting input, and therefore it goes out with a non-inverting gain to the output. And in part B, all right, in part B, we are told that the op-amp is non-ideal. It now has I plus, I minus, and V offset. So now we have I plus, we also have I minus, and we have V offset, and V offset is introduced at the non-inverting input as VI naught here. Right? So this is the non-ideality now. And we are told to find out the DC voltage at the output when the input is 0. So we kill Vs and evaluate the voltage at the output due to these three non-ideality terms. So V out is equal to V out V offset plus V out due to I minus plus V out due to I plus. Exactly what we have done in question 1. Alright, we're going to do it in question 2 again. Alright, so here we evaluate V offset. V offset now goes to the output. Sorry, V offset goes to the output. V offset multiplied by the non-inverting gain R2 over R1 plus 1. Okay, why? Because I plus and I minus is 0, and therefore the voltage goes directly to the non-inverting input and appears at the output through the non-inverting gain amplifier. Realize again, RS is not playing a part because there's no current flowing through RS, because we are only evaluating V offset. Alright? So by superposition, we are dealing one DC at one time. Alright? Then we add up with I minus. When we are dealing with I minus, we kill I plus, we kill V offset, and therefore I minus has to flow through R2 because this node is virtual ground. Why is it virtual ground? V offset is not there. I plus also not there. Therefore, the voltage at this node is as good as ground. Right? If this is ground, this becomes virtual ground. And if this is virtual ground, both end of the resistor R1 is at 0. So there's no current flowing through R1. And therefore, the current I minus has to flow through R2. And in so doing, causes the voltage on the right to be more positive than that of the left, but the left end goes to virtual ground, means the voltage at the right is the voltage that is across your output. And therefore that voltage is I minus R2. Okay? Then you add up with the I plus component to the output. So when I plus flows through from ground to RS, through RS, it incurs voltage across RS. So this current is flowing out from ground. And as it flows out from ground, it incurs voltage across RS, where the voltage here is more positive than the voltage on this side, causing the voltage at this node to be more negative than ground. Now since the offset voltage here is 0, this voltage appears at the non-inverting input, and that value is minus I plus times RS multiplied to the output by the non-inverting gain. Okay, are you all following? Somewhere around there. Your eyelid is getting heavier because now it's about 2:50. This is the best time to sleep. And do you realize recently the weather in Singapore is cool? It's quite good, huh? I think there's a tilt in the equator. If this goes on, we'll be having winter soon. Alright, so anyway, so this is what we have. Alright, so now we, this is part B. So this is the answer to part B. So let's take a look at part C. Alright, in part C, what happened? We are told that the op-amp is non-ideal and the signal Vs appear on top of the fact that the three non-ideal DC source also is there. So basically, V out is actually V out of part A plus V out of part B. Alright? It's basically V out of part A plus V out of part B, because all the four components, Vs, I plus, I minus, V offset, all appear now. Alright? So you just sum the two, and basically this is your V out AC plus your V out DC. So this is basically your V out DC, and this is your V out AC. Okay? So you have part C, just put the two equations together because we can use superposition, and therefore part C is just the sum of these two. Alright? Then we look at part B. So ever in the exam, this one is a gift. Correct? Part A plus part B is called part C. Alright, man. Christmas gift. Or in this case, Chinese New Year. Okay, let's take a look at part D. In part D, okay, we are given that the resistor, alright, is 100K here and 25K over here. Alright? And therefore the non-inverting gain is 1 plus 100K over 25K. So the non-inverting gain will be 5. Right? But inverting gain will be minus 4. But the non-inverting gain is 5, which is what we're going to look at because all these are non-inverting. So therefore that portion will become 5. Right? So in part D we are asked to find out the minimum DC offset at the output, and therefore we can find out what the value of RS. So in this case, to minimize the DC voltage at the output, we don't need to look at the AC, so we just look at part B again. So we take part B and evaluate part B. So part B gives you V out DC is equal to V offset, okay, multiplied by 5, because its gain is 5, alright, and V offset is at this point equal to 2 millivolt, is given to you is 2 millivolt, so this is 2 millivolt, plus I minus. Now this is where you need to find out what I minus and I plus is. We are given that I bias is equal to I plus I minus divided by 2, and this value is 100 nano. And we also told that I offset is equal to I plus minus I minus is equal to minus 40 nano. So if you look at these two equations, alright, I plus I minus over 2 is equal to 100. I offset is this minus this is equal to minus 40. You have two equations, two unknown. I plus and I minus is unknown, but we have two equations. And therefore we can write the value of I plus and I minus. We know that I plus must be equal to 80 nano. By solving it, I minus must be equal to 120 nano. And if you realize that when we take I plus, you add up with I minus, you get 200 nano. Divided by 2, you get 100 nano. Right? If you take I plus minus I minus, you get minus 40. So therefore I plus and I minus are these values. Okay? By solving the two unknown equations, you get the two unknown I plus and I minus. So here, you can now make use of this equation. Take I minus, which is 120 nano, multiply it by R2, which is 100K. Alright? And then you minus I plus, which is 80 nano, multiply it by RS, multiply it by 5, because the gain is 5, alright? And therefore you have this equation. And in order to minimize this, we make V out DC equal to 0. The minimum value for V out DC is 0. So we equate 0 is equal to 2 millivolt multiplied by 5 plus 120 nano multiplied by 100K minus 80 nano multiplied by 5 times RS. Okay, so we can solve for RS, and RS will be equal to what? 55K. Alright? You'll be able to solve it and get 55K here. Alright? Any violent objection? No? Okay. So let's move on to question 3. Okay? So in question 3, we are given an op-amp connected as an inverting amplifier with a gain of minus 50, introduced by using two resistors, 100K and 2K, in negative feedback. And to the non-inverting input, there is a 2K resistor connected to ground. And again, this op-amp, in this case, is a non-ideal op-amp, and it has I bias is equal to 10 micro with I offset being 0, which tells you that I plus is equal to I minus is equal to 10 micro. Alright? And therefore, we can draw this as this. Right? We will end up with op-amp that is inverting. Alright? So you have this op-amp, inverting op-amp with 2K here, 100K here, and you have a resistor here, which is 2K to ground. Alright? And so this is, and you also have two current, I minus, which is 10 micro, and I plus, which is also 10 micro, because I offset is 0, so I plus must be equal to I minus is equal to I bias, right? And we also told that there's an offset. So this offset here is 10 millivolts. And this is precisely what we have. And we also given slew rate is equal to 1 volt per microsecond. And we are asked to find out the DC component at the output caused by the non-ideal parameters. Since we're only talking about the non-ideal parameters, the AC is assumed to be 0, or the input is assumed to be 0. And basically, we just want to find out the voltage at the output due to the DC. So the output due to the DC is equal to the three terms again. Realize that in this case, slew rate is not required because there is no AC signal coming in. So the slew rate is given to you as a bogus, just to throw you off guard. Alright? So no need to use the slew rate. So to find out V out DC, we just simply take the offset voltage, okay, multiply by the non-inverting gain, plus the I plus, which is 10 micro, flowing out from ground, permeating across the resistor, appearing at the non-inverting input with a negative sign because it's flowing out from ground, and then it goes through a non-inverting gain, and then you multiply, then you look at I minus. I minus would be a current that is again 100 nano, 10 micro, alright, multiply by R2, which is 100K to the output, and this is all that you have. And if you evaluate this, you get a voltage that is 490 millivolts. Now, why suddenly I didn't put in the V offset, I plus, I minus, and all this? Is because I introduced this so that you can think about how did I get 51? Where does this term come from? Why minus 10 micro? Why times 2K and all this? Make you do a little bit of work, otherwise you just copy the answer. Correct? Yeah? So you get this answer. Any question? Why 51? Why 51? Why? 1 plus the feedback resistor over 2K, right? Right? Okay, so this is what it is. Now, again, if I bring you back to the value of Rx, remember, if I don't have this offset voltage, if I remove this offset, what is the DC at the output? If there is no input offset, if I remove the 10 millivolt, so I remove this term. One term will be negative, one term will be positive. What is the voltage at the output? I look at you, you look at me, we see love.
Is it only left with VI plus and VI minus?
Yes. VI plus and VI minus term will come in, right? Because we are not evaluating the offset. So?
So you may cancel out if you change the resistance.
Yes. If we make this resistance 2K in parallel with 100K, which is what we were working on in the class, right? If we make a resistor here that is of a value 2K and 100K, we will be able to cancel out these two current and resulting in an output that is 0. But now we can't. Why? Because this resistor is not 2K in parallel 100K. But it's close. 2K in parallel 100K is almost 2K. It's slightly lesser than 2K, 1.9 something. Right? So that means to say, when the current 10 micro flow through 1.9 something K, you will get a voltage, and the current flowing through K, you will get a voltage. Then this voltage will be more negative than this voltage. Alright? So therefore this minus this will have a more negative value across here. When multiplied by the non-inverting gain, you get a voltage at the output that is more negative. And that's why if you look at this term, this times this is more than 100K. This is 100K, this is more than 100K, right? So obviously this term is more than this. So the net result is a negative value. And it will appear at the output as a negative value. So it's a negative, but the value is very small. Because 2K is almost the same as 1.9 something. So it's better to have a resistor than not having a resistor. Imagine this resistor is not here. What would happen? Then this term is not around. Then you have a voltage that is very much higher. Right? So this is just to offset the difference so that the output becomes smaller. Now obviously in production, I plus and I minus will never be equal. There's no chance of having precisely the same current, right? And therefore, there's no need to put the precise resistance of a 2K and 100K in parallel because we will never be having the same current after all. So there's no way you can cancel. So you might as well put a resistor that is close and try to help to bring the voltage down. All right? So basically, that's what it is. All right? Okay? Okay, let's take a look at question 4. So in question 4, we have the same question as we have seen last week. All right, we put two amplifiers in cascade. But this time, there's something different is that we put in an offset for both of them. And each of this offset is 2 millivolt, plus, minus 2 millivolt. Right? And the input is a 25 millivolt sinusoidal. Alright? And the gain of the first stage is 20. So R1 over R2 is 20. Inverting, so it's minus R2 over R1 for the gain. And the output is limited to plus and minus 14 volt. That means to say the output come no closer to the power supply, each of the power supply. So minus 15 plus 15 minus 1 volt on, and in either direction. So it's plus minus 14 volt. Okay. And each of the op-amp is of course connected to a plus minus supply. Huh? right, or plus minus 15 volt. So this is what we have. And we know that when we enter a signal like this, a sinusoidal at the input here, at the output is inverted. We have a gain of 20. So therefore the amplitude here is 20 times that of the input. So now this is 500 millivolt peak. So peak to peak is 1 volt. All right, peak to peak is 1 volt, but peak value is 500 millivolt. Okay, and then it goes to the output again, and therefore the output and the input will be in phase. When it is going through a positive excursion signal, the output also goes through a positive excursion signal. All right, so this is what we have, and therefore we can write the equation that V out is equal to V in multiplied by the first gain stage R2 over R1 multiplied by the second gain stage R4 over R3. Alright, so this is for the input. Then we take, when we're dealing with the V offset, we kill V in, we kill the second offset, we only deal with the first offset, and the first offset goes out by going through the first gain stage, which is R2 over R1 plus 1 multiplied by the non-inverting gain of the second stage. And then we look at the second gain stage, second offset to the output, and therefore it's just R4 over R3 plus R plus 1. Okay, so this is the total voltage at the output. The output consists of 3 terms because there's 3 sources: input, first offset, second offset to the output. So again, by superposition, we deal with it one at a time, assuming that the output lies within the linear range. Okay? So if you look at this, in the absence of the signal V in, if we kill V in, then we need to process what is the DC voltage at the output. Let's take a look at the DC voltage at the output. The first offset goes through a non-inverting gain to this point. Then it goes through an inverting gain, and therefore this is your first offset to the output. The second offset, we kill V in, we kill V offset. The voltage here is 0, no contribution from either source. So the voltage here is 0. So when the voltage here is 0, V offset of the second stage, C, a non-inverting amplifier. So V offset goes to the output with a non-inverting gain. Okay, so the 3 components, you sum it up, is at the output now. So if you, V in is not there, this offset is negative because there's a minus sign here. This offset is positive. Which of these 2 terms is larger in magnitude? The second or the third term? Hello, you all are getting very slow. You all are in cloud time. Oh, okay. Third is more positive, this is more negative, but the magnitude of this is bigger than this, right? The second term has a bigger magnitude than the third term, right? Correct now? Because this offset is being multiplied by 2 gain stages, whereas this offset is being multiplied by a single gain stage. Obviously, this component is more negative than this. So the net result is a DC value that is non-zero. It will be a negative value now. Right? It's a negative DC. If you recall tutorial 1 last week, question 5, we have 2 signals coming in, one AC, one DC, and what happened at the output? We have 11 millivolt, where the output is shifted by 11 millivolt, right? And the AC is riding on that DC. So here, same thing. Now, the DC is negative. So this is a negative DC. This is your 0. Alright? So now, our AC that is inverted now goes in through another inversion and it comes out non-inverted with this AC riding on it. As I increase the signal strength, this is going to increase until I hit negative 14. Further increase in the gain R4 and R5 is going to increase the output signal further. And any increase, the output will not be able to go across minus 14, but instead it will be flattened out. It will be clipped. Right? Therefore, it will go through a nonlinear region, right? It's nonlinear, and therefore, this is not what we want. We want the output to remain in the linear region, and therefore, we have to equate this by putting a voltage at the output as minus 14 is equal to minus 25 millivolt multiplied by the first gain stage, which is 20 with a minus, multiplied by the second gain stage, which we don't know, we need to find out, plus the offset of the first offset, which is 2 millivolt, multiplied by 21, because 20 R2 over R1, which is 20 plus 1, so it's 21, multiplied by minus R4 over R3, plus 2 millivolt, multiplied by R4 over R3 plus 1. So this is your equation, and you need to solve this. And there's only one unknown, which is R4 over R3. When you solve this value is 26. So that is your answer. Okay? Any reason why I use minus 14 and minus 25 millivolt? Any reason why I use minus 14 and minus 25? Can I use plus 14 and plus 25 millivolt? In tutorial 1, we have almost the same question where the DC offset wasn't there. Remember? Right? It's the same question. In tutorial 1, we have the same question, just that without the DC offset. And in that solution, we found that the resistor is 28. The ratio was 28. Remember? Now, the gain is 26. So I give you another solution. No, sorry. I give you another wrong answer. I make this plus 14. I make this plus 25. And the ratio will become equal to 30. Right? So if you choose this to be plus 14 and this to be plus 25, the gain will be 30. In other words, if I choose this to be R4 over R3 of 30, then this signal will touch positive 14. When this touch positive 14, the negative cycle will go further down, and therefore it will be clipped. Right? And therefore the output will be distorted if you have a gain of plus 30. This is exactly why we use minus 14 and minus 25, because when the input is minus 25, it corresponds to this point 500 millivolt, and this 500 millivolt will correspond to this point minus 14, okay, by going through this gain stage, because 500 millivolt, all right, when multiplied by 26 will give you minus 14 when you subtract another voltage of minus some value. And you can go and calculate this minus some value by going through this portion here. Okay? Alright? In other words, actually if you go and calculate, you'll find that the voltage here is minus 1 volt. Okay? So minus 1 volt to minus 14, you have a 13 volt. Alright? You have 13 volt negative cycle. So in order to get 13 from 500, so 500 must multiply by 26 to give you 13, right? That is why that is the value. So you cannot use plus 14 and correspond to a plus 25 millivolt. You must equate it to the negative because the DC has been shifted down. Okay? Alright? Okay. Now let's take a look at question 5. So in question 5, we are told that we have an amplifier with the inverting amplifier again. And again is 50 R, okay? And the input is a sinusoidal that is 10 millivolt peak. 10 millivolt peak. Right? And this time, no offset is given, right? Except there's a slew rate that is 1 volt per microsecond, which in terms is equal to 1 megavolt per second. All right? So 1 megavolt per second corresponds to 1 volt per microsecond. And then it's going to go out inverted with a peak value that is 500 millivolt, 500 millivolt on either side. So therefore it's a peak-to-peak voltage of 1 volt, a sine wave of peak-to-peak of 1 volt. Alright? And then we know that if the input is, if V in is equal to 10 millivolt cos omega t, because it's a sinusoidal. So a sinusoidal can be a cos wave or a sine wave. Alright? So I purposely use cos wave because everyone assumed that a sinusoidal is a sine wave. A sinusoidal can be a cos wave. Alright? So I write a cosine input now. And therefore at the output, alright, you have a negative cosine wave. Alright? So okay, I should start from the peak value, but now mine is shifted. Alright? So anyway, at the output, I have this. I can write my output V out is equal to minus 50 times 10 millivolt, okay, cos omega t. So this is my output, okay, my output. And I know that the slew rate must be greater or equal to the maximum rate of change at the output. Right? And therefore I can now write the equation of dV out dt. And this is equal to what? Is equal to minus 50, okay, 10 times 10 millivolt, okay, omega, okay, sine omega t. Forget about the sine. I don't remember what happened when we differentiate, so I just know that it's going to be cos or sine, the difference. I bring out the omega, alright? So this is what we have. And we know that the slew rate, which is 10 megavolt, 1 megavolt, must be greater or equal to the maximum rate of change of this. So the maximum value of this is when sine omega t is equal to 1. Alright? So this is it. Alright? So to find out omega max, so omega max will be equal to this 1 megavolt divided by 50 divided by 10 millivolt. Alright? So F max is equal to 1 megavolt divided by the gain, alright, divided by 10 millivolt divided by 2 pi. Forget about the volt. Alright? So you have this. This is your result. And if you find out this is 318 kilohertz. Alright? And if we really want to see the formula, this formula is the slew rate divided by the closed loop gain, right, divided by the amplitude of the input signal times 2 pi. So if we look at this, okay, if we look at this, if I keep the input frequency fixed at 318, alright, and I increase the magnitude of the input signal, increase this. Slew rate of the op-amp remains the same. The closed loop gain, it remains the same. Alright? Then it will go into slew rate limitation if I increase this. So if I increase this, I have to decrease the gain because the net must remain the same. And if you look into the next tutorial, tutorial 3, there will be questions related to this. So it's good to know how to derive this equation because it will help you with the analysis. Okay? Any violent objection? Okay? So this is question 5A. Okay, let's take a look at what happened if I now pump in a signal that is not sinusoidal, but instead is a triangular waveform. So I'm going to pump in a triangular waveform into this gain of minus 50, and the output is going to be an inverted version of the input with a gain that is 50 times bigger. So if this is 10 millivolt, then this will be 500 milli. Alright? So this is your input and output waveform. Alright? So now I'm going to draw a line. And this slope is 1 volt per microsecond. Okay? I'm going to draw a line through the zero crossing. And I'm also going to draw a line here, and this is minus 500 millivolt, and this is plus 500 millivolt. Okay? And I'm going to increase the input frequency. Take the input sonic triangular wave, I increase the frequency. Right? Same amplitude, I increase the frequency. As I increase the frequency, the zero crossing point get closer and closer to one another. Am I right? That's how we increase the frequency, right? So as I increase in frequency, there will be a point in which this slope become this slope. Alright? But when that happens, of course, the frequency is very much higher. And of course, the zero crossing point becomes closer to one another because the frequency would have increased. So now this slope will be 1 microsecond. So as it comes down, it is also coming down at minus 1 volt per microsecond. Right? So I take the center point, I divide this into 2. This will be 1 microsecond. And this side will also be 1 microsecond. Because this is plus 500 millivolt, sorry, minus 500 millivolt, and this is plus 500 millivolt. That means to say from top to bottom is 1 volt. And it incurs 1 volt with 1 microsecond. So if it comes up and goes down, it will incur 2 microseconds. And therefore the period of this waveform is equal to 2 microseconds. Therefore the frequency of this triangular wave is 500 kilohertz because it's just 1 over t. Right? So therefore, the frequency of the triangular wave, the maximum frequency of the triangular wave, alright, that will be slew rate limited is when the frequency is at 500 K. Anything higher than that, what happens? What happens when the frequency increases beyond 500 K? The output will not be able to follow the gain of this amplification. In other words, the slope will always be this slope, So as I increase in frequency, the output zero crossing must come closer and closer to one another, right? Correct? So therefore, what would happen? Suppose this point is fixed. Then what would happen is, as the frequency increase, the slope remain the same. So the slope remain the same, right? You end up with a peak point that is much lower. I have another slope that is parallel to this, right? And therefore you see that the amplitude has decreased, but the slope remains the same because it's slew rate limited, right? Therefore, as I increase the frequency, the amplitude start to decrease beyond this frequency 500K. Alright? And therefore, that is slew rate limited. You are not getting the same gain anymore. You're not going to get 500 millivolt anymore. Alright? Because of this slew rate limitation. Alright? Any question? For a moment, when you look at this, it looks like a voltage source, a battery, 1/T. So if anyone don't follow this, what the hell is this? How come frequency of the triangular wave is equal to a battery?
Redundant.
Okay, so now let's take a look at what happens if I pump in a square wave. Again, 10 millivolts to the top, 10 millivolts to the bottom, right? If I pump in this into this amplifier, it will come out as this. This slope is 1 volt per microsecond. This slope is minus 1 volt per microsecond. So the output is slew rate limited. Why? Because the input is a square wave, and when it transverse from minus 10 millivolt to plus 10 millivolt, it goes through a rate of change that is infinite, because it incurs a voltage of 20 millivolt at 0 time. Correct? So the dVdt at that point is infinity. So the slew rate is limited, it cannot be infinity, and therefore during that point it will just slew at 1 volt per microsecond. The voltage at the output is still 500 millivolt minus, and this is what you have. So as I increase the frequency of the square wave, the output is still 500 on either side, right? But these two slopes become closer and closer to one another because the frequency increase, right? So when these two slopes touch one another, what is this frequency? The frequency will be 500K. The frequency will be the same as what we have done just now. It will be 500K because now the flat top will disappear. Because the two edges will touch one another, it will still give you 500 millivolt on either side. But that will be the maximum where the voltage will still comply to the gain. Beyond that, again, the amplitude will start decreasing with increasing frequency of the square wave. So the square wave will become triangular wave at the output. Okay? Any question? If not, we stop here. We leave